Welcome to 10 minutes CS. For one, cousins in binary tree 2. Given the root of a binary tree, we need to replace the values of each node in tree with the sum of all its cousin values. Two nodes of binary tree are cousins if they have same depth but with different parents. And we need to return the root of the modified tree at last. So who will be cousins here? Seventh node will be cousin for node 1 and 10, and the sum of 1 and 10 will be the value of the seventh node after modification. So here we see the for 5 we don't have any cousin because it doesn't have a parent, so it will be 0. So every time for the root value we know that its value will be 0 after modification because it won't have a cousin. And then for 4 and 9 we see that they don't have a cousin, they are in siblings but they don't have any other node which has a different parent, so their values will also be 0 0. But for 1 and 10 we see a node 7 which is at same level but have a different parent, so they will be modified to 7 and 7. And for node 7 we see we have to write the sum of 10 and 1. So we know we have to do a level order traversal here, that will be BFS. So we will need a queue and we will that do the same BFS here. But how will we find out the values that we need to modify? So one thing we can see here from this level, let's say we can have the sum of that level, so it will be 1 plus 10 plus 7. And to find the value of, let's say, this node, we can subtract the value of that node in itself, so we will get the remaining value, that will be the value of its cousins. Similarly, if we take this 10th node, so we have the sum as 1 plus 10 plus 7. If we subtract the value of its sibling nodes, that is 1 and 10, so we will get the value of its cousin, that will be 7. So while doing BFS, we will need the sum of that level, and after doing the sum of that level, we will need the sum of its siblings. So instead of finding this sum, we can do another loop over the nodes, and while doing that traversal, we can reduce the sum that we found, that is the level sum, with the sum of the nodes, and we can assign the sum that we found here, that will be the resultant, to the nodes. So the nodes value will be changed to the resultant, and we can keep on doing same, and at the last we can just return the root. Let's look at the code for better understanding. For our BFS, we will need a queue, and we will add our root to the queue, and we will change the root value to 0 in the start itself. So this will be 0, and we will continue to do our BFS unless our queue is empty. So we first find the size of our queue at that end, and we will have sum equal to 0. And while going over each of those nodes, we will add those nodes to our level queue so that we can process them later. And in the first for loop, we will keep on adding it to our sum, and we will add the values to our queue. So let's say this is our queue and this is our buffer queue, that is the level queue. So initially we will add 5 to it, and we poll our 5 from that, and we will add it to our level queue, and we will check if its left is not null, so we will add it to our sum. So sum will be added, and after that we will add it to our queue, and similarly we will do with our right node also. So this will be 9. Once we have done this, we will go to our next for loop where we will do the modifications in our binary tree. So let's take the temporary sum as the sum. So this will be 9 plus 4 13, and we see if the left node is not null, so we will reduce it from our temporary sum its value. That means here we are reducing the values of the sibling nodes. So we reduce it by 4, and similarly we see the right node is also not null, so we will reduce its value from this. Now our temporary sum is 0. Now we will assign whatever temporary sum is left, that is the sum which is left for the cousin nodes, to our node dot left dot value, that is this one. So this will be 0, and again this will be 0. Let's go for next iteration. Now we will take this node and we will pop out, and we will check for the left and right node. We will add it to our queue, and we will add this node to our level queue, and we will add it to our sum also, 1 plus 10. Similarly we will do with this node, we will pop it, we will add it to our level queue, and we will add the sum of its level nodes here. So this will be 18. Now we have assigned our temporary sum to 18, and we are checking for this node right now, and while doing so we will check if its left is not null and right is not null. We will reduce those sibling values from our temporary sum, and once that is done we are left with 7, and we will assign it to our left and right node both. Similarly we will do for our 9th node. So here we will come to this node, we will see this will again be assigned to sum. So this is 18 now. We see that its left node is null, so this won't be this if condition won't be proceeded. We see that the node dot right is not equal to null, so we will subtract it from there. Now we are left with 11. So if the left node is null, so we won't proceed with this if condition, and we see that the node dot right is not equal to null, so we will assign this value to our right node. Now once that is done, we again go to our queue, we pop this one, we see that the left and right are both null, so nothing is added to the sum remains 0. Similarly we can go for this node, so this will also be doesn't have a left or right node, next level is empty. Similarly for 7, next level is empty. Once all that is done, we can return the root, that will be this. So our tree will look like 0 0 0 7 7 and 11. Now what will be the time and space complexity for this algorithm? We are using BFS, and we have to go through all the nodes in the binary tree. Let's say it has n number of nodes, so we have to go through all of them, and each level we are proceeding twice, so that will be 2 of n, that is almost equal to big O of n. And for space complexity we are using Q. At max it can have all the nodes at a particular level. Let's say if it's if there are n nodes, we can take it as big O of n. And we have another Q here which will also be having all the nodes, so it will be 2 of big O of n, that is almost equal to big O of n. Thank you for watching.